So this next section, we're now looking at acid-base character of salt solutions. And you're familiar with salts. They are primarily ionic compounds. And up until now, we have just thought about them as a salt, something we put on our food or something that we make from a titration. But we've never thought about salts as acids or bases before. The ions that make up the salts can be acidic ions or they can be basic ions because they may be the conjugate acid of a weak base or the conjugate base of a weak acid. So, how can you tell if a salt is going to have a pH effect in solution? You look at the formula for the salt and you identify the ions. Are they conjugates of weak acids or bases? Conjugate bases of strong acids don't affect pH. So we've talked about these before, things like HCl. It breaks apart into a hydrogen ion and a chloride ion, and it's a one-way ionization in the strong acid. So this chloride ion has no interest at all in going backwards to make HCl. So it just hangs out here, and it will not react with water to try and pull a proton off there, and it won't take the proton that's available in solution. Another example of a strong acid is nitric acid. So again, this goes in a one-way street, H plus NO3 minus, and the nitrate ion does not have any pH effect because it will not act as a base. Conjugate bases of strong acids don't affect pH, they just sit there. Then you have to decide, do I have an acid that's a conjugate acid of weak base, or do I have a base that's a conjugate base of weak acid, or do I have both of those in there? And if you have both, you have a hot mess of equilibria, and we won't do any calculations with that in this class. But we will decide which is stronger, but we won't actually do the math. So let's look at the first example. Cations, which are the conjugate acid of weak bases, can behave as an acid. So our classic example of a weak base was ammonia. So now our classic example is the ammonium ion. So if I have an ammonium ion, it can go into equilibrium to make a proton plus ammonia. This can go both ways. Ammonia is the base. It can grab that proton and go back and make the conjugate acid. So, as we saw in the very last section, we can determine the Ka for the ammonium ion from the Kb for the base. So, let's go ahead and do that. So, Ka for ammonium is equal to Kw divided by Kb for ammonia. So, that's equal to 1.0 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th, and that's equal to 5.6 times 10 to the negative 10th, and that's equal to my Ka. So anytime we have the conjugate acid of a weak base, then we can find the Ka for that. Now, how do you start to recognize these? You're going to recognize them by their names because most of the weak bases have names that end in "ene" or "ine," I-N-E, and the conjugate acids of those bases will have names that end in "-ium," ammonium, morphinium, strychninium, those kinds of things, butylaminium. So when the name ends in "-ium," it is the conjugate acid of the weak base. It's the cation. And this can be part of the salt. So let's look at a typical problem now. What's the pH of 0.1 molar ammonium chloride solution? Well, this goes back to your nomenclature for Chem 111. So the first thing we do is write the proper formula, ammonium chloride, NH4Cl. This breaks apart in a one-way street to make the ammonium ion and the chloride ion. Those two ions are now floating around in solution. Now we look at them and say, well, what are they, acid-base speaking? This is the conjugate acid of a weak base, so it will act like an acid. this is the conjugate base of a strong acid, it has no pH effect. So it will not do anything to affect the pH. So this is what's going to control the pH of the solution. So now, when we think about this, if I have 0.1 molar ammonium chloride, now I have 0.1 molar ammonium and 0.1 molar chloride. And the chloride ion sitting in solution has nothing to do with anything relative to pH. So now we can set up the ice chart for the equilibrium that's going to control the pH. And this is where it gets messy. You know how to do the math for an ice chart. But now this ice chart is the ammonium ion in equilibrium with ammonia plus a hydrogen ion. So this will be an acidic solution. So we set up our chart. We have 0.1 molar ammonium, 0 and 0. This changes. It goes down by X, up by X, and up by X. At equilibrium, I have 0.1 minus X, X, and X. Because I'm making the proton, this is an acid equilibrium. Because it's an acid equilibrium, I need the Ka. Now, we did this on the previous page. We said Ka was Kw divided by Kb for ammonia, and so our Ka is 5.6 times 10 to the negative 10th. So now I have my Ka, I have my ice chart. Now this is exactly what we've been doing for 3 chapters. Same old, same old. 5.6 times 10 to the negative 10th is equal to the ammonia, X, times the hydrogen concentration, X, divided by ammonium. So 5.6 times 10 to the negative 11th is equal to X squared. X is the square root of 5.6 times 10 to the negative 11th. It's equal to the hydrogen concentration, which is 7.5 times 10 to the negative 6th molar. So the pH is minus the log of the hydrogen ion concentration, 7.5 times 10 to the negative 6th molar, is 5.13. Now, this is where you stop and think. 5.13, that's less than 7 at 25 degrees C, so it's an acid, and this is an acid. Ammonium is an acid, so that seems like a reasonable answer. And the only thing that is new or challenging here is the chemistry, and this is the hard part. It's recognizing that ammonium is an acid because it's the conjugate acid of a weak base. But the math is exactly what we've been doing before. Okay? Let's go ahead and have you do the next one on your whiteboards.